The ground moved in a place it was never supposed to move, and the scientists watching the data in real time went quiet, in a way that people who study earthquakes for a living almost never go quiet. Not because the earthquake was the largest ever recorded in Canada, it was not. Not because the casualty numbers were catastrophic in the way that earthquake casualties in densely populated regions can be. They were not. The scientists went quiet because of what the earthquake said about what is coming. Because in seismology, the event itself is rarely the whole story. The event is the message. And this particular message, arriving from a fault system that most Canadians had never heard of, written in the specific language of ground motion and depth and rupture geometry that seismologists spend careers learning to read, was saying something that the models had not predicted with this timing, this location, this character. It was saying that the accumulated stress in the crust beneath Western Canada had reached a threshold that the community of Earth scientists monitoring that region had known was approaching, but had not expected to cross, yet. The word yet is doing an enormous amount of work in that sentence. And understanding exactly what it means requires going back several hundred years to a coastline that looks peaceful from the surface and is anything but peaceful underneath it. The Cascadia subduction zone runs for roughly 1,000 kilometers along the Pacific coast of North America, from Northern California up through Oregon and Washington and into British Columbia. It is the boundary where the Juan de Fuca tectonic plate, a remnant of the ancient Farallon plate that once covered most of the eastern Pacific, is diving beneath the North American plate at a rate of approximately 4 centimeters per year. 4 centimeters sounds trivial. Over a human lifetime, it amounts to roughly 3 meters of convergence. Over 300 years, it is 12 meters. Over 500 years, it is 20 meters of accumulated strain energy locked into a fault interface that stretches across the seafloor off the Pacific Northwest coast, held in place by friction, building pressure, storing the energy of continental collision the way a spring stores the energy of compression, waiting for the friction to fail. The last time that friction failed completely along the full length of the Cascadia subduction zone was January 26, 1700. The earthquake that resulted was magnitude 9 or greater, one of the most powerful earthquakes in the geological record of North America, rupturing the full length of the subduction zone in a matter of minutes and generating a tsunami that crossed the Pacific and was recorded with sufficient precision in Japanese historical documents to allow modern scientists to calculate its timing and therefore work backward to determine the exact date and approximate magnitude of the parent earthquake. The Japanese records describe an orphan tsunami, a tsunami that arrived on the Japanese coast without the earthquake shaking that typically precedes a tsunami generated close to Japan. The wave had travelled thousands of kilometres across the open Pacific from its source off the coast of what is now Oregon and Washington. It arrived in Japan approximately 10 hours after the earthquake that generated it. The earthquake itself was not felt in Japan, only the wave arrived. And the wave was large enough to cause documented damage to Japanese coastal communities in 1700, 325 years before the earthquake that just shook Canada was recorded on seismometers around the world. 325 years of accumulated strain. That is the number that makes seismologists go quiet. The earthquake that struck Canada was not on the Cascadia megathrust itself. This is the first thing that needs to be understood clearly, because the distinction matters enormously for interpreting what the event means. The shaking originated on what geologists call an intraplate fault, a fault that exists within the overriding North American plate rather than at the interface between the plates. Intraplate earthquakes in the Pacific Northwest occur in a stress environment that is directly shaped by the Cascadia subduction process. The Juan de Fuca plate pushing beneath North America does not simply slide smoothly under and disappear. It deforms the overlying crust, creates regions of compression and tension, and loads faults that would otherwise be geologically quiet, with stresses generated by the subduction process happening below them. The earthquake that just happened was, in the language seismologists use, a stress transfer event. The subduction zone below shifted fractionally, redistributing stress through the crust above it, and a fault that had been accumulating that redistributed stress for years released it in seconds. That mechanism, stress transfer from a locked subduction zone to the faults embedded in the overriding plate, is one of the reasons the scientific community watches intraplate earthquakes in subduction zone regions with particular attention. They are not random. They are not independent of the larger tectonic system. They are, in a very real sense, the subduction zone communicating through the crust. And what this particular communication said, when the seismologists analysed the focal mechanism, the depth, the rupture direction, and the relationship of the event to the known stress field of the region, was that the stress in the crust of southwestern British Columbia is currently elevated above what background loading from the subduction process alone would produce. Something has been adding to the baseline. Something has been pushing the system closer to the threshold at which the next major rupture becomes possible. And the earthquake that just happened is evidence that the threshold is being approached from below, that the crust is responding to that approach, that the seismic system is not dormant. The specific location of the earthquake matters. It occurred in a region of British Columbia that sits within what geologists have designated as a high seismic hazard zone, not because of the frequency of historical earthquakes recorded since European settlement of the region, which is a short and seismically quiet record, but because of the paleoseismic evidence preserved in the geological record going back thousands of years. Paleoseismology is the science of reading earthquakes from sediment layers, from drowned forests, from tsunami deposits preserved in coastal marshes, from sudden subsidence events recorded in the stratigraphy of coastal lowlands. The Pacific coast of British Columbia and Washington state is covered in this kind of evidence. Core samples taken from coastal marshes up and down the coast show repeated cycles of the same pattern. A layer of soil representing a coastal meadow or low forest. Then, a sudden transition to marine sediment, indicating that the land dropped abruptly and the sea flooded in. Then another layer of soil as the land slowly rebounded and vegetation re-established. Then another abrupt transition. Then another rebound. The pattern repeats every 200 to 500 years. Each abrupt transition represents a megathrust earthquake large enough to drop the coast by a metre or more in seconds. Each layer of marine sediment above a terrestrial layer is a geological fingerprint of a Cascadia rupture. The paleoseismic record suggests that the Cascadia subduction zone has produced full-length ruptures, the kind capable of magnitude 9 or greater earthquakes approximately every 200 to 500 years over the past 10,000 years. The average recurrence interval across the full geological record is approximately 240 years. The last full rupture was 325 years ago. The arithmetic is uncomfortable. 325 years since the last event, an average recurrence interval of 240 years. The zone is, by that measure, 85 years past its average recurrence interval. Seismologists are careful about this language because recurrence intervals have wide uncertainty ranges, and because saying the zone is overdue implies a regularity in earthquake timing that the geological record does not fully support. But the alternative phrasing, that the zone is in the latter portion of its typical interseismic period, that the probability of rupture in any given decade is substantially higher now than it was a century ago, is one that the scientific community does support. The earthquake that just hit Canada is occurring in that context, in that tectonic moment. The depth of the earthquake provided additional information that the seismology community found significant. It occurred at approximately 23 kilometers depth, which places it in the lower crust of the North American plate, above the subducting Juan de Fuca slab. At that depth, the rock is under enormous pressure, and the temperatures are high enough that some minerals that are brittle at the surface begin to behave more plastically, more capable of slow deformation rather than sudden rupture. Earthquakes at this depth in the crust of a subduction zone, overriding plate, are associated with conditions that geologists call episodic tremor and slip, a phenomenon discovered in the Pacific Northwest in the early 2000s that fundamentally changed how seismologists think about the subduction cycle. Episodic tremor and slip, abbreviated ETS, is a process that occurs at the deep transition zone between the locked and freely slipping portions of the subduction interface, at depths typically between 25 and 45 kilometers. In this zone, the plate interface does not lock and release dramatically, like the shallow locked zone that produces megathrust earthquakes. Instead, it slips slowly and periodically, producing a pattern of low-frequency seismic tremor that is too weak to be felt by people, but is detectable by sensitive seismometers. Each ETS event involves several centimeters of slow slip occurring over days to weeks, releasing some accumulated strain from the deep portion of the subduction zone. The Pacific Northwest experiences ETS events on a remarkably regular schedule, approximately every 14 months, a regularity that has no equivalent in any other tectonic setting on Earth, and that scientists are still working to fully explain. The most recent ETS event in the Pacific Northwest region occurred approximately 3 months before the earthquake that just struck Canada. 3 months. The relationship between ETS events and the stress state of the overlying crust is an active research question. Some models suggest that ETS events transfer stress upward into the overriding plate, potentially loading the faults in the crust above the slow slip zone. If that model is correct, the earthquake that just occurred is partly a response to the most recent ETS event. It is the crust above the deep slip zone responding to a stress increment delivered from below. The GPS network that covers the Pacific Northwest and British Columbia is one of the densest networks of continuous geodetic monitoring on Earth. Hundreds of continuously operating GPS receivers are embedded in the bedrock and soil of the region, measuring their positions to millimeter accuracy on a daily basis. Over years of observation, these receivers have traced the motion of the North American plate surface as it is pushed and deformed by the subduction process beneath it. During the locked interseismic period between major ruptures, the GPS data shows a characteristic pattern. The coastline moves slowly inland away from the trench as the locked subduction zone pulls the surface down and inward. The inland regions show less motion. The entire surface is being deformed like a compressed spring, storing elastic strain energy that will be released when the fault finally ruptures. The GPS data for the Pacific Northwest has been showing this interseismic deformation pattern continuously since the network was established in the 1990s. The rates are consistent with the accumulation of strain energy at a pace that, integrated over the 325 years since the last megathrust event, represents an enormous stored energy budget. After the earthquake that just struck Canada, the GPS receivers nearest the epicenter showed a small but measurable coseismic offset, a sudden displacement of the ground surface at the moment of rupture. The direction and magnitude of that offset were consistent with the focal mechanism derived from the seismic waveforms, confirming the rupture geometry and providing additional constraint on the stress change produced by the event. More significantly, the GPS data from the weeks preceding the earthquake, when examined in retrospect, showed a subtle acceleration in the rate of surface deformation in the region surrounding the eventual epicenter, subtle enough that it had not triggered any automated alert, subtle enough that it would not have been noticed without the earthquake to direct attention back to the preceding data, but measurable. The crust had been moving slightly faster than the long-term background rate in the weeks before the earthquake, a pattern consistent with accelerating strain accumulation on the fault that eventually ruptured. This kind of precursory signal is exactly what earthquake scientists have been searching for decades, the reliable, detectable indication that a fault is approaching rupture. The problem is that the signal was only recognizable in retrospect. It was buried in the noise of normal geodetic variability until the earthquake that followed it gave it meaning. This is the central unsolved problem of earthquake science, and it has been unsolved for as long as the field has existed. Earthquakes are almost never predicted in the specific sense that the public understands prediction, a statement that an earthquake of a given magnitude will occur in a given location within a given time frame. The physics of fault rupture involves processes at scales ranging from the atomic to the continental, operating over timescales from milliseconds to centuries, in a medium that is heterogeneous, poorly sampled, and inaccessible to direct observation below the first few kilometers of depth. The conditions that determine exactly when a fault that is close to failure will actually fail are sensitive to factors that cannot be measured with sufficient precision at sufficient depth. The stress state of the fault at the point of nucleation, the pore fluid pressure in the rock surrounding the fault, the microscale roughness of the fault surface that determines how friction evolves as slip begins. None of these can be measured with the resolution required to predict rupture timing. The earthquake that just hit Canada, like virtually every earthquake before it, was not predicted. It was responded to. The response from the scientific community was immediate and systematic. Within minutes of the earthquake, seismological observatories across North America were processing the waveform data arriving at their stations from the event. The USGS National Earthquake Information Center in Golden, Colorado, which monitors seismic activity globally around the clock, had a preliminary location and magnitude estimate published within 12 minutes of the origin time. That estimate was refined repeatedly in the hours that followed as more data arrived from more distant stations, and as the complex task of determining the depth and rupture geometry from the waveforms was completed by automated systems and then verified by human analysts. The process of fully characterizing a significant earthquake, from the initial automatic detection to the final authoritative source parameters, now takes hours rather than the days or weeks it once required. That acceleration is the product of decades of investment in seismic network infrastructure and in the computational systems that process the network data. The aftershock sequence that followed the main earthquake provided additional scientific information that was being analysed simultaneously with the main event characterization. Aftershocks are not random. They cluster around the rupture zone of the main event, and their distribution in space and time tells seismologists about the geometry of the rupture, the stress changes it produced in the surrounding crust, and the likelihood of subsequent events. The Omori-Utsu law, one of the oldest empirical relationships in seismology, describes how aftershock rates decay with time following a main earthquake. The rate is high immediately after the main shock and decays as a power law function of time, meaning that the 1000th aftershock occurs much later than the 100th, which occurs much later than the 10th, which occurs much later than the 1st. This predictable statistical behaviour allows seismologists to forecast the expected number and magnitude distribution of aftershocks in the hours and days following a significant earthquake, providing emergency managers with probabilistic information about the ongoing hazard that is more useful than either alarming speculation or false reassurance. The aftershock forecast issued following the Canadian earthquake included a probability estimate for a magnitude 6 or greater aftershock in the 30 days following the main event that was higher than the base rate for the region by a factor that made emergency managers in British Columbia and Washington State pay attention. A magnitude 6 aftershock in the vicinity of the main event, occurring in a region where the building stock and infrastructure had already experienced strong ground motion from the main earthquake, can cause damage and injury that in some cases exceeds the impact of the original event, because structures weakened by the main shock are more vulnerable to the strong shaking of a large aftershock. This is not a theoretical concern. Historical earthquake sequences around the world have repeatedly demonstrated that aftershocks cause disproportionate harm in communities where the main event left structures standing but compromised. The combination of apparent survival of the main event and the assumption that the danger has passed is one of the most dangerous cognitive states a community can occupy in the hours and days following a significant earthquake. The ground motion produced by the Canadian earthquake was recorded by accelerometers embedded in buildings across the region, part of a structural health monitoring system that has been progressively expanded in the Pacific Northwest and British Columbia over the past 2 decades. These instruments, installed in bridges, hospitals, government buildings, and high-rise structures, measure the acceleration of the building at multiple floors during seismic shaking and transmit that data in real time to engineering assessment centres. After an earthquake, structural engineers can examine the records from these instruments to determine whether a building experienced ground motion within its design envelope, whether any permanent deformation occurred, and whether the building's structural response was consistent with its design assumptions. Buildings that appear undamaged from the exterior can show instrumental records that indicate the structure absorbed more energy than its design anticipated, suggesting that a subsequent earthquake of similar size might cause visible damage or collapse. The instrumental records from the Canadian earthquake were being reviewed by structural engineering teams across the region in the hours and days after the event, generating assessments that would inform decisions about which structures should be inspected before being reoccupied and which could be reopened immediately. The tsunami question was addressed within the first minutes of the earthquake. The West Coast and Alaska Tsunami Warning Center, which monitors seismic activity in the Pacific in real time and issues tsunami warnings for the west coast of North America, evaluated the preliminary earthquake parameters against their decision criteria and determined that the earthquake did not meet the threshold for a Pacific-wide tsunami warning. The depth, location, and mechanism of the event were inconsistent with the seafloor deformation geometry required to generate a significant tsunami. This determination was correct and was communicated quickly to coastal emergency managers who had been alerted to monitor the situation. The no tsunami determination does not mean that the Cascadia system cannot generate a tsunami. It means that this particular earthquake, on this particular fault, with this particular mechanism, did not do so. The megathrust earthquake that the paleoseismic record indicates is building in the locked zone of the Cascadia subduction zone will generate a tsunami. When that earthquake occurs, the seafloor off the coast of British Columbia and Washington and Oregon will deform by meters in seconds, displacing an enormous volume of water and generating tsunami waves that will reach the coast of the Pacific Northwest in as little as 15 to 20 minutes in some locations. The no tsunami message from the Canadian earthquake should not be mistaken for a statement about the tsunami hazard of the region. It is a statement about this specific earthquake, not about the system that generated it. The building codes and land use planning frameworks of the Pacific Northwest and British Columbia incorporate the Cascadia earthquake and tsunami hazard to varying degrees, depending on jurisdiction, date of adoption, and political will at the time regulations were written. The modern seismic design provisions in the building codes of Washington, Oregon, and British Columbia are among the most stringent in North America, reflecting the scientific understanding of the hazard that has accumulated over the past several decades. Structures built to current code in these jurisdictions are designed to resist the ground shaking expected from a Cascadia megathrust event without collapsing, providing life safety protection for occupants. They are not designed to be undamaged after such an event. The distinction between collapse prevention and damage limitation is one that most building occupants do not make when they think about earthquake safety, but it is one that determines what a community looks like in the hours and days after a major earthquake. How much of its infrastructure is functional, how quickly it can support its own recovery, and how many of its residents are alive but homeless. The older building stock, the unreinforced masonry structures, the concrete buildings constructed before modern seismic provisions were adopted, the soft-story wood frame apartment buildings that represent a significant fraction of housing in cities like Seattle, Portland, and Vancouver are a different story. These structures were not designed for the ground shaking the Cascadia system can produce. Some of them are dangerous in earthquakes significantly smaller than a full Cascadia rupture. The retrofit programs that would address this vulnerability have been under discussion in various forms for years. The pace of implementation has been constrained by cost, by the complexity of coordinating mandatory retrofit programs across jurisdictions with different political environments, and by the perennial challenge of mobilizing public and political will to invest in reducing a risk that has not materialized within living memory. The earthquake that just hit Canada was a reminder. It was not the earthquake that will test those buildings at full scale. That test is still coming. The Cascadia earthquake and tsunami planning documents produced by state and provincial emergency management agencies paint a picture of post-event conditions that is sobering even in the planning documents, which are written to be reassuring about the preparedness measures in place. The projected impact of a full Cascadia rupture on the Pacific Northwest includes the destruction of a significant fraction of unreinforced masonry buildings in affected cities, damage to highway infrastructure that isolates coastal communities for days to weeks, disruption to electricity and natural gas systems across the region, and tsunami inundation of coastal areas that have been mapped with increasing precision as tsunami modelling has improved. The economic losses from such an event have been estimated in the hundreds of billions of dollars. The loss of life, In a scenario where a major earthquake strikes during a period of high occupancy in vulnerable buildings and is followed by a tsunami that reaches coastal areas before all residents can evacuate, is projected in scenarios that emergency managers do not publish in their public communications, but that inform the scale of the response planning. The Canadian earthquake did not produce those outcomes, but it refreshed the awareness within the scientific community and among the emergency managers who work with that community daily that the system capable of producing those outcomes is not dormant, it is active, it is loaded, it has been accumulating strain for 325 years. And the earthquake that just happened, on a fault within the overriding plate, at a depth consistent with stress transfer from the subduction interface, in a region where the GPS data shows active interseismic deformation, is a data point that fits the model of a subduction zone system that is in the latter portion of its interseismic cycle. The scientific literature on the Cascadia system has been accumulating for decades, and it has converged on several conclusions that are held with high confidence within the earth science community. The Juan de Fuca plate is subducting beneath North America. The subduction interface is currently locked in its shallow portion, accumulating strain. The locked zone last ruptured in 1700. The geological record documents repeated ruptures with recurrence intervals in the range of 200 to 500 years. The next full rupture will produce a magnitude 9 or greater earthquake. That earthquake will generate a tsunami. The shaking and tsunami will affect the Pacific coast of North America, from northern California to British Columbia, with intensity that will depend on the specific rupture geometry, but that will be severe across a broad area. These conclusions are not contested within the scientific community. The uncertainty is in the timing, not in whether, in when. The earthquake that just hit Canada did not answer the timing question. No single earthquake can answer that question, but it contributed a data point to the ongoing scientific effort to understand the current state of the Cascadia system, and that data point was not reassuring. The stress field analysis derived from the earthquake's focal mechanism is consistent with a crust that is under elevated compressive stress in the direction aligned with the Cascadia convergence. The depth and location of the event are consistent with stress transfer from the locked subduction interface. The GPS precursory signal, subtle as it was, is consistent with accelerating strain accumulation on faults in the overriding plate. None of these observations proves that the Cascadia megathrust is closer to rupture than it was before the earthquake, but none of them suggests it is further away. And the scientists who study this system for a living, who spend their careers reading the data coming off the network of seismometers and GPS receivers and ocean bottom pressure sensors that monitor the Cascadia zone, went quiet when the data came in, because the data was consistent with the thing they have been watching for, not confirming it, not predicting it, but consistent with it in a way that the data does not always have to be. The ocean bottom pressure sensors that have been deployed along the Cascadia Trench in recent years represent one of the most important advances in monitoring this system since continuous GPS was established in the 1990s. These instruments, anchored to the seafloor at depths of several kilometers, measure the pressure of the water column above them with sufficient precision to detect the vertical displacement of the seafloor by centimeters. When a locked fault on the subduction interface slips, even slowly, even by amounts too small to register as a felt earthquake, the seafloor moves. The pressure sensors record that movement as a change in the water column height above them. The network is not yet dense enough to provide complete coverage of the Cascadia Trench. Gaps exist, particularly in the northern portion of the zone off the coast of British Columbia, where the combination of remote location and logistical challenges in maintaining deep-sea instrumentation has slowed the expansion of coverage. But where the sensors exist, they are providing a kind of direct observation of the subduction interface that was simply not possible before their deployment. They are watching the locked zone from below, from the ocean side, reading the small motions of a surface that will one day move catastrophically, and that is, in the meantime, accumulating the energy for that motion 1 millimeter at a time. The data from those sensors in the period surrounding the Canadian earthquake was being reviewed with particular attention by the oceanographic and geodetic teams responsible for the network. The review was precautionary. The sensors had not recorded any anomalous seafloor displacement prior to the earthquake. but precautionary review of all available data following a significant tectonic event in a monitored region is standard practice, and in this case, the review was motivated by the knowledge that any signal, however small, that might contribute to understanding the relationship between the intraplate earthquake that just occurred and the state of the locked zone below would be scientifically valuable. The subduction zone does not announce its intentions. It expresses them slowly, in the cumulative behaviour of a system under stress, readable only to those who know the language. The community of people who live in the Cascadia hazard zone without knowing the language of that system numbers in the millions. The metropolitan areas of Seattle, Tacoma, Portland, Salem, Eugene, and Vancouver, British Columbia, together represent one of the most seismically exposed concentrations of population in North America. The awareness of earthquake hazard in these communities is higher than in many other at-risk regions of the country, partly because of the work of science communicators and emergency managers who have been working for years to translate the geological reality into public understanding. The phrase, "the really big one," drawn from a widely read New Yorker article published in 2015 that brought the Cascadia hazard to national attention, has become part of the cultural vocabulary of the Pacific Northwest. People in Seattle know that the really big one is coming. Many of them have earthquake preparedness kits. Many have thought about where they would go if the ground started shaking. The gap between that general awareness and the specific actionable preparedness that would determine outcomes during and after a major event is still substantial. The specific preparedness gap that earthquake scientists and emergency managers most want to close is the knowledge of what to do in the first 30 seconds of a major earthquake. The Shake Alert early warning system, which was fully deployed across the Pacific Northwest in the years preceding 2026, provides warning times ranging from a few seconds to roughly a minute for people at various distances from the earthquake's epicenter. A minute of warning before strong shaking arrives is enough time to drop, cover, and hold on, to move away from windows, to get under a sturdy table or desk. It is not enough time to evacuate a building. The protective action of drop, cover, and hold on is well established in the scientific literature as the correct response to earthquake shaking for people in structures. It reduces injuries from falling objects and structural elements. It is simple. It can be executed in the first seconds of shaking without requiring any prior knowledge of the specific earthquake or its location. And it is still not universally known or practiced by the residents of the Cascadia hazard zone. The earthquake that just hit Canada activated Shake Alert across the affected region. Alerts were delivered to cell phones, to integrated systems in schools and hospitals, to transportation management centres monitoring highway conditions. The alerts gave residents seconds of warning before the strongest shaking arrived. In the areas closest to the epicenter, the warning time was shorter because the P waves, the faster compressional waves that travel ahead of the more destructive S waves and surface waves, had less distance to travel before the S waves arrived behind them. In areas further from the epicenter, the warning times were longer, providing more opportunity for automated systems to execute protective actions like stopping trains, opening fire station doors, and pausing surgical procedures. The system worked as designed. The question that the earthquake raised about the system is not whether it worked, but whether it can work at the scale that a Cascadia megathrust event will require. A full Cascadia rupture will produce strong shaking across a much larger area than the Canadian earthquake, will stress the communications infrastructure that carries the alerts, and will occur close enough to many populated areas that warning times will be measured in seconds rather than minutes. The system will activate. The question is whether the population has been sufficiently educated about how to respond to that activation, that the seconds of warning translate into protective actions rather than confusion. The schools of the Pacific Northwest have been incorporating earthquake preparedness drills into their routine since before the Shake Alert system existed. The earthquake, drop, cover, and hold on protocol is practiced by children across the region with the regularity that fire drills have been practiced for generations. This is the right approach, and it represents a meaningful improvement in preparedness compared to a generation ago. The children who have practiced earthquake drills in school will carry that knowledge into adulthood and into their own households. The adults who did not grow up with those drills and who have not sought out preparedness information independently represent a different challenge. Reaching adults with earthquake preparedness information in a way that changes their behaviour, rather than simply adding to their awareness, is one of the persistent challenges of emergency preparedness communication. Information alone does not change behaviour. The bridge between knowing what to do and actually doing it in the chaotic, disorienting first seconds of a major earthquake is built through practice, through repetition, through making the correct response automatic rather than deliberate. The infrastructure vulnerability that concerns earthquake engineers most in the Pacific Northwest is not primarily the buildings. Modern buildings in the region are increasingly built to codes that address the Cascadia hazard. The infrastructure that concerns engineers is the lifeline systems, the water, electricity, natural gas, and transportation networks that the population depends on for survival in the aftermath of a major earthquake. These networks are extensive, aging in many components, and difficult to retrofit comprehensively because they span entire regions and are owned by dozens of different utilities and government agencies. The unreinforced masonry walls that might collapse during a major earthquake in older parts of Seattle or Portland or Vancouver are dangerous and important to address. But a collapsed building kills the people inside it. A failed water system, unable to deliver potable water to a region of several million people in the days and weeks following a major earthquake, affects everyone. The Cascadia Planning District, a multi-jurisdictional planning body created specifically to coordinate preparedness for the Cascadia scenario across the state and provincial boundaries that a major event will not respect, has identified the water system resilience as one of its highest priorities. Progress has been made, comprehensive solution remains years away. The natural gas infrastructure is a particular concern because of the fire risk following a major earthquake. Post-earthquake fires are one of the most destructive secondary hazards associated with large urban earthquakes. The 1906 San Francisco earthquake, one of the most studied earthquakes in American history, caused more of its total destruction through fire than through ground shaking. The fires started at dozens of locations simultaneously when broken gas lines ignited, overwhelmed a fire department whose water supply had been severed by the earthquake, and burned for 3 days through the city. Modern cities in earthquake zones have installed automatic gas shutoff systems at critical nodes in the distribution network, and modern gas meters in many jurisdictions now include seismic shutoff valves that close automatically when strong shaking is detected. But the coverage of these protections is incomplete. Sections of the distribution network in the oldest parts of Pacific Northwest cities use pipe materials and connection types that are known to be vulnerable to earthquake damage. The risk of post-earthquake fire is real, is understood by fire departments across the region, and is incorporated into their planning. The gap between planning and capacity to respond is one that a major earthquake will reveal with brutal efficiency. The Canadian earthquake activated a response across scientific, emergency management, and public communications channels that was rapid, coordinated, and informed by the decades of preparedness planning that the Cascadia hazard has generated. Within hours, briefings were being delivered to government officials at the municipal, provincial, and federal level. Scientific experts were appearing in media to provide context and analysis. Social media was doing what social media does in the immediate aftermath of significant events, mixing accurate information with speculation and misinformation in proportions that made the task of the official communications channels more difficult than it would have been in a pre-social media information environment. The challenge of communicating accurate scientific uncertainty, the genuine, honest message that this earthquake is significant, but that it does not allow prediction of the timing of a future megathrust, is one that competes in the public attention environment with simpler, more alarming, and less accurate framings. The honest scientific message about the Cascadia system after this earthquake is exactly what it was before this earthquake, stated with slightly more urgency. The system is locked. It is accumulating strain. It has done so before, repeatedly, over thousands of years. It will rupture again. The rupture will produce a major earthquake and a tsunami. The communities of the Pacific Northwest have been building their preparedness for this scenario for years and have made meaningful progress. The preparedness is not complete. The earthquake that just happened is a reminder that the system is not dormant, that the stress in the crust above the locked zone is responding to the accumulation of strain, and that the interval between now and the next major Cascadia event is shorter than it was 325 years ago by exactly 325 years. The seismometers that recorded the Canadian earthquake are still running. They run continuously, sampling the ground motion at dozens of times per second, transmitting that data to processing centers in real time, feeding the algorithms that detect, locate, and characterize earthquakes anywhere in the monitored network. The GPS receivers are still measuring. The ocean bottom pressure sensors are still watching the seafloor. The shake alert system is still armed and waiting. The paleoseismologists are still coring the coastal marshes, reading the sediment layers, extending the record of past events deeper into geological time. The earth scientists studying the Cascadia system are still at their desks, still watching the data, still building the understanding of a system that will one day test everything the Pacific Northwest has built and everyone who lives there in ways that no other natural hazard in North America can match. They went quiet when the data came in, because the data was telling them something they have been trained to hear. Not the answer to the timing question. The timing question does not have an answer that the current state of earthquake science can provide. What the data was telling them is that the system is speaking, that the stress is high enough that the crust above the locked zone is responding, that the earthquake that just happened is not background noise, it is signal. And the people whose job is to listen to that signal, who have built careers on learning to distinguish noise from signal in the geological record of a planet that has been moving and rupturing and rebuilding itself for 4.5 billion years, went quiet, because what they heard was signal. The ground moved in a place it was never supposed to move, and somewhere beneath the seafloor off the coast of British Columbia, the locked interface between two tectonic plates continued its silent accumulation, unmoved by the earthquake above it, unchanged by the scientific attention it has received, indifferent to the communities built on the surface above it, storing the energy of 325 years of convergence and waiting, with the patience of geology, for the friction to fail. The friction will fail. That sentence is not speculation. It is not the dramatic language of disaster entertainment. It is the consensus statement of every seismologist who has studied the Cascadia system with sufficient depth to have an informed opinion. The debate within the scientific community is not about whether the Cascadia subduction zone will produce another megathrust earthquake. It is about the details of when, how large, which portions of the fault will rupture together, and what the ground motion distribution will look like across the Pacific Northwest when it does. Those details matter enormously for planning purposes. A full-length rupture from Northern California to British Columbia produces a different damage distribution than a partial rupture limited to the northern or southern segment. The shaking in Seattle from a full rupture centered off the Washington coast is different from the shaking produced by a rupture centered off the Oregon coast. The tsunami run-up heights along specific stretches of coastline depend on the precise geometry of the seafloor deformation, which depends on which portions of the locked interface slip by how much. These are not academic distinctions. They are the parameters that determine which buildings collapse, which coastal communities are inundated before their residents can evacuate, which highways remain passable for emergency response, and which water systems survive intact enough to support recovery operations in the critical first weeks after the event. The scientific effort to constrain those parameters has been ongoing for decades and has accelerated significantly in the years since the Tohoku earthquake and tsunami struck Japan in March 2011. The Tohoku event was a watershed moment for subduction zone science globally, not because it was the first megathrust earthquake to be studied with modern instrumentation, but because the density and quality of instrumentation in Japan and the thoroughness of Japanese scientific documentation produced a dataset of unprecedented richness about how a locked subduction zone behaves in the minutes before, during, and after a magnitude 9 rupture. The lessons from Tohoku have been applied directly to Cascadia research. The Japanese experience demonstrated that the locked zone off Tohoku had been storing more strain energy than pre-event models had suggested, that the slip during the earthquake was larger than expected in the deepest portions of the locked zone, and that the resulting seafloor displacement and tsunami were larger than the pre-event hazard assessments had indicated. The post-Tohoku revision of Cascadia hazard assessments incorporated similar considerations, and the revised assessments generally indicated higher potential ground motions and larger potential tsunamis than the pre-Tohoku estimates. The city of Vancouver, British Columbia, sits in a tectonic setting that differs in important ways from Seattle and Portland, and those differences matter for how a Cascadia megathrust event would affect it. Vancouver is located further north along the subduction zone, in a region where the geometry of the subducting Juan de Fuca plate transitions into the geometry of the Explorer plate, a smaller and more complex tectonic fragment that interacts with North America in ways that are less well understood than the central portion of the Cascadia system. The earthquake that just struck Canada occurred in British Columbia, in the complex tectonic environment north of the main Cascadia zone, and its occurrence is a reminder that the seismic hazard of the region is not limited to the Cascadia megathrust alone. The overlying crust of British Columbia contains numerous faults that can produce damaging earthquakes independently of the subduction process, and the stress field in that crust is influenced by the subduction in ways that make the regional hazard more complex than a simple two-fault model would suggest. The Fraser River Delta, on which much of metropolitan Vancouver is built, presents a specific engineering challenge that amplifies the already significant seismic hazard of the region. The delta sediments are young, water-saturated, and in many places susceptible to liquefaction during strong earthquake shaking. Liquefaction occurs when saturated granular sediments are subjected to cyclic shear stress from seismic waves and temporarily lose their strength, behaving for a period as a fluid rather than a solid. Buildings founded on liquefiable sediments can settle, tilt, or overturn during liquefaction, even if the buildings themselves are structurally intact. Underground utilities embedded in liquefiable sediments can float upward, rupturing connections and rising above the surface. The phenomenon is well documented in dozens of earthquake events worldwide, including the 1964 Alaska earthquake and the 1964 Niigata earthquake in Japan, both of which produced dramatic liquefaction in delta and coastal plain sediments. The Fraser River Delta sediments have been mapped for liquefaction susceptibility, and the maps show extensive zones of high and very high susceptibility underlying populated portions of Richmond, Delta, and other municipalities in the metropolitan area. The building codes address this hazard through foundation requirements in high susceptibility zones, but the existing building stock in those areas includes many structures built before modern liquefaction-aware codes were adopted. The seismic microzonation of the Pacific Northwest, the detailed mapping of how different soil conditions affect the amplification and modification of seismic waves as they travel from bedrock to the surface, is one of the most practically important products of applied earthquake science for the region. Seismic waves travel efficiently through hard rock, but are amplified, slowed, and modified when they enter softer sedimentary materials. A site underlain by soft bay mud or river delta deposits may experience ground shaking that is 3 to 5 times more intense than a nearby site underlain by hard rock, even though both sites are equidistant from the earthquake. This amplification effect is why the Marina district of San Francisco, built on bayfill, experienced some of the most severe damage in the 1989 Loma Prieta earthquake, while nearby neighborhoods on bedrock were less severely affected. The Loma Prieta earthquake was a magnitude 6.9 event, occurring on a fault approximately 100 kilometers from San Francisco. The Cascadia megathrust will be a magnitude 9 or greater event, occurring on a fault system that underlies the entire region. The amplification effects in soft soil areas of Seattle, Portland, and Vancouver during a Cascadia event will be proportionally larger and will affect proportionally more of those cities than the Loma Prieta amplification affected San Francisco. The specific neighborhoods of Seattle that sit on the filled tidelands and glacial outwash deposits of the Duwamish River Valley and the South Seattle Industrial District are among the most extensively studied high amplification zones in the Pacific Northwest. Research conducted by the University of Washington and the USGS has characterized the shaking amplification in these areas with increasing precision using arrays of seismometers that record the response of the soft sediments to distant earthquakes and to the small local earthquakes that occur regularly in the Puget Sound region. The data from those arrays has been used to calibrate the ground motion models used in seismic hazard assessments and building code development. It has also been used to produce maps that show, neighbourhood by neighbourhood, what the expected shaking intensity would be during a major earthquake. Those maps are publicly available. They are used by planners and engineers. They are not prominently featured in the public communications about earthquake risk that reach most residents of the affected areas. The economic geography of seismic risk in the Pacific Northwest reflects a pattern that earthquake researchers have observed in other seismically hazardous regions around the world. The neighbourhoods with the highest physical vulnerability to earthquake damage, those built on liquefiable or high amplification soils, underlain by older building stock, housing residents with lower average incomes and fewer resources to prepare or recover, tend to be the same neighbourhoods that have historically been underserved by the institutional investments in preparedness, retrofit programs, and community resilience that reduce vulnerability. The relationship between economic marginalisation and physical disaster vulnerability is not unique to earthquakes. It appears in flood risk, in wildfire risk, in heatwave mortality. In the Cascadia context, it means that the communities most likely to experience the most severe impacts from a major earthquake are also the communities least positioned to absorb those impacts, without long-term consequences for the health, economic stability, and social cohesion of their residents. The retrofit programs that have been implemented in the Pacific Northwest have made meaningful progress on specific building types. The mandatory soft-story retrofit program implemented in Seattle targeted a category of wood frame apartment buildings with open ground floor configurations, parking garages, or commercial spaces with minimal structural walls that are known to be vulnerable to collapse during moderate to strong earthquakes. These buildings failed in large numbers during the 1994 Northridge earthquake in California and the 1989 Loma Prieta earthquake, and the pattern of their failure was sufficiently well understood that engineering solutions for retrofit were available and relatively cost-effective compared to full replacement. The Seattle program required owners of these buildings to complete seismic evaluations and, where indicated, seismic retrofits within defined timelines. Compliance rates have been tracked and enforcement mechanisms have been applied to owners who did not meet the deadlines. Progress has been made. The inventory of soft-story buildings in Seattle that remain unretrofitted is smaller than it was 10 years ago. It is not zero. The unreinforced masonry buildings that represent a significant fraction of the older commercial and residential building stock in Portland, Oregon, present a different and in some ways more difficult retrofit challenge. Portland has a larger inventory of unreinforced masonry buildings than Seattle, partly because of different historical development patterns, and partly because the mandatory retrofit programs that Seattle has implemented have not been matched by equivalent programs in Portland. Unreinforced masonry, brick walls held together by mortar without steel reinforcement, is one of the most dangerous building materials in an earthquake. The walls are heavy, brittle, and poorly connected to the floors and roof of the building. During strong shaking they crack, separate from each other, and fall outward onto the street or collapse inward onto the occupants. The death toll from unreinforced masonry building failures in historical earthquakes around the world is enormous. In the 1988 Spitak earthquake in Armenia, unreinforced masonry and poorly constructed concrete frame buildings collapsed wholesale, killing approximately 25,000 people in a region with a population comparable to a medium-sized American city. The ground motion levels that caused those collapses in Armenia are within the range that Portland could experience during a Cascadia megathrust event. The inventory of unreinforced masonry buildings in Portland that have not been retrofitted and that currently house residents, employees, and visitors represents one of the most significant unaddressed life safety vulnerabilities in the Pacific Northwest. The political economy of mandatory seismic retrofit is one of the most challenging problems in earthquake risk reduction policy. The buildings that need to be retrofitted are privately owned. The cost of retrofitting them falls on the owners, who may pass some portion of that cost to tenants through rent increases, creating a tension between life safety goals and housing affordability goals in cities where housing costs are already a major political issue. The benefit of the retrofit accrues primarily to the future occupants of the building during the earthquake, who are not the same people as the current occupants and who cannot effectively advocate for the investment. The earthquake itself, which would demonstrate the value of the retrofit investment with brutal clarity, is an event that the political system finds difficult to plan for when the probability in any given year is low, even though the cumulative probability over decades is high. The result of this political economy is that mandatory retrofit programs are adopted slowly, implemented over long timelines, and are often less comprehensive than the engineering assessment of the problem would recommend. The tsunami preparedness dimension of the Cascadia hazard adds a geographic specificity to the risk that the earthquake preparedness discussion sometimes obscures. The earthquake shaking from a Cascadia megathrust will be broadly distributed across the Pacific Northwest, affecting inland cities like Seattle and Portland that are tens to hundreds of kilometers from the coast. The tsunami generated by the same earthquake will be a coastal phenomenon, affecting the communities along the Pacific coast of Washington, Oregon, and British Columbia that sit within the inundation zone mapped for the Cascadia scenario. Those communities are smaller in total population than the inland urban centres, but they are no less real in their vulnerability and in the specific character of the threat they face. The tsunami warning for those communities in a Cascadia scenario will arrive from the earthquake shaking itself rather than from an external alert system. The Shake Alert early warning message will tell coastal residents that a major earthquake is occurring. The knowledge that a major earthquake in the Cascadia zone generates a tsunami that reaches the coast in 15 to 20 minutes in some locations and in 30 to 45 minutes in others is the warning that should trigger immediate vertical evacuation. The chain from earthquake shaking to tsunami awareness to evacuation decision to physical movement to high ground needs to execute in 15 minutes or less for the nearest coastal communities. For communities like Seaside and Cannon Beach in Oregon, or the communities on the Long Beach Peninsula in Washington, or Tofino and Ucluelet on the west coast of Vancouver Island, the tsunami inundation zones extend well inland, and the high ground that represents safety is in some cases several kilometres from the areas most at risk. 15 minutes of warning time and several kilometres of distance to travel is a scenario that requires pre-planning, pre-positioned evacuation routes, and a population that has internalised the earthquake means evacuate now message so thoroughly that the decision requires no deliberation in the moment. The vertical evacuation structures that have been built and proposed along the Cascadia-affected coast represent an acknowledgement that for some communities, horizontal evacuation to high ground within the available warning time is not possible for all residents. Mobility-limited individuals, elderly residents, people in hospitals or care facilities cannot always travel the distances required in the time available. Vertical evacuation structures are reinforced buildings or purpose-built towers designed to withstand tsunami inundation and to provide refuge for people who cannot reach high ground. The first purpose-built tsunami vertical evacuation structure in the continental United States was constructed in Tokeland, Washington, completed in 2016. It is a reinforced concrete structure designed to remain standing and provide refuge during the tsunami inundation expected at that location from a Cascadia megathrust event. Additional structures have been proposed and in some cases funded for other at-risk communities. The number of completed structures relative to the number that would be needed to provide comprehensive coverage for the at-risk coastal population is a ratio that the tsunami preparedness community tracks with a combination of professional concern and the pragmatic acceptance that progress on complex infrastructure problems moves slowly. The ocean conditions along the Cascadia-affected coast add a layer of complexity to tsunami preparedness that is not always incorporated into the public communication about the hazard. The Pacific coast of the Northwest is not uniformly accessible or uniformly developed. Long stretches of coastline are backed by steep terrain that provides natural protection and that makes evacuation physically straightforward for the small populations in those areas. Other stretches, particularly the low-lying estuarine areas where rivers meet the Pacific, are extensively developed, heavily populated seasonally by tourists, and sit in topographic settings where the tsunami inundation zone extends far inland along the river valleys. The Tillamook Bay area in Oregon, the Grays Harbor area in Washington, the multiple coastal estuaries along the British Columbia coast, all represent combinations of low topography, river valley amplification of tsunami run-up, and population concentration that place them among the highest priority areas for preparedness investment. The seasonal population component is particularly challenging for preparedness planning. The permanent residents of a coastal community may be well prepared, may know the evacuation routes, may have the earthquake means evacuate now message internalized. The tourists who fill coastal hotels, rental properties, and campgrounds during summer weekends may have no awareness of the hazard at all. The research effort to improve understanding of the Cascadia system continues on multiple fronts simultaneously. The Cascadia Initiative, an ocean-bottom seismometer deployment that placed instruments on the seafloor off the Pacific Northwest coast for the purpose of imaging the subducting Juan de Fuca plate and monitoring its seismicity, produced years of data that fundamentally improved the scientific understanding of the structure and behavior of the subduction zone. The data from those instruments revealed details of the locked zone geometry, the distribution of tremor and slow slip, and the seismicity patterns in the subducting slab that were not accessible from land-based instruments alone. The Cascadia Initiative ended as a formal program, but the scientific analysis of the data it collected is ongoing and continues to generate publications that refine the hazard assessments. New proposals for ocean bottom monitoring of the Cascadia zone are being developed, informed by the lessons of the Cascadia Initiative and by the advances in ocean bottom instrumentation technology that have occurred in the years since the original deployment. The deep drilling program component of the international scientific effort to understand subduction zones has targeted other subduction zones around the world for direct sampling of the fault zone materials at depth. Direct samples from the fault interface of an active subduction zone, retrieved by drilling through the overlying sediments and into the fault gouge itself, provide information about the mineralogy, pore fluid chemistry, and physical properties of the fault zone material that cannot be obtained by any other means. The properties of the fault material determine how it behaves during slow slip and during rapid co-seismic slip. Understanding those properties is essential for understanding why some portions of a fault are locked and accumulate strain, while other portions slip aseismically. The Cascadia subduction zone has been proposed as a target for deep drilling at several points in the history of the scientific drilling program. A drill hole into the Cascadia fault zone at a strategic location would provide data of extraordinary scientific value. The logistical and financial challenges of ocean drilling at the depths and locations required have prevented this from being accomplished to date. The modelling effort that translates scientific understanding of the Cascadia system into the ground motion predictions used for building code development and emergency planning has advanced substantially in recent years. The next generation attenuation relationships, empirical equations that predict ground motion amplitude as a function of earthquake magnitude, distance, depth, and site conditions, have been revised multiple times as new data from earthquakes around the world has accumulated. Each revision has incorporated data from additional megathrust earthquakes, progressively improving the reliability of the predictions at the large magnitudes and long distances most relevant to Cascadia scenario planning. The current generation of ground motion models is substantially more reliable than the models available when the first modern Cascadia hazard assessments were produced in the 1990s. But uncertainty remains, particularly for the very large magnitudes and the specific tectonic setting of the Cascadia zone. And that uncertainty is propagated through into the hazard assessments and building code provisions in ways that require careful probabilistic treatment. The probabilistic seismic hazard analysis framework that underlies modern building codes represents one of the most sophisticated applications of probability theory to engineering practice that exists. The framework integrates information about the rates of earthquakes of different magnitudes on all relevant faults in a region, the ground motions those earthquakes would produce at a site of interest, the uncertainty in all of those quantities, and produces a probability distribution of ground motion levels that might be experienced at the site over a defined time period. The building code provisions for a given region are derived from specific points on that probability distribution, typically the ground motion level that has a 2% probability of being exceeded in 50 years, which corresponds approximately to a return period of 2,500 years. This probabilistic framework is powerful because it accounts for all sources of seismic hazard in a region simultaneously, including both the frequent smaller earthquakes on nearby faults and the infrequent but potentially catastrophic events on the Cascadia megathrust. and weights them by their probability of occurrence and their contribution to ground motion at the site. The practical consequence of this framework for a building in downtown Seattle is that the seismic design forces in the building code are derived from a probabilistic assessment that accounts for the Cascadia megathrust as a major contributor to the 2,500-year ground motion level. A building designed to the current Seattle building code is designed to resist, without collapse, the ground motion associated with a Cascadia megathrust earthquake at the appropriate distance and for the specific soil conditions at the building site. This does not mean the building will be undamaged. It means that the building will remain standing and will provide life safety protection for its occupants. The distinction matters for understanding what the building stock of Seattle will look like after a Cascadia event. Most modern code-compliant buildings will be damaged. Some will be significantly damaged. Very few will collapse. The older buildings, those built before modern seismic codes were adopted, or those that have not been retrofitted, present a different picture. And the infrastructure systems on which the occupants of all those buildings depend for water, sanitation, energy, and transportation will be damaged in patterns that are harder to predict and that will determine the pace and character of recovery. The recovery planning for a Cascadia megathrust event is one of the most complex long-term planning exercises that emergency management agencies in the Pacific Northwest have undertaken. The Cascadia subduction zone planning effort, involving multiple states, provinces, federal agencies, and tribal nations, has produced planning documents that describe the expected impacts across multiple sectors and the actions required to support recovery across a timeline measured in months to years. The recovery timeline for a Cascadia event is not a matter of weeks. The damage to infrastructure, the displacement of populations from damaged housing, the disruption to economic activity, and the psychological impact on affected communities will play out over a period that historical analogy from comparable events suggests will extend for years. The Tohoku earthquake and tsunami of 2011, which struck a wealthy, well-prepared nation with a highly functional government, still left some coastal communities in Japan in active recovery mode 5 years after the event. The Cascadia event will strike a region with more total economic resources than the Tohoku-affected area, but with infrastructure systems that are older, more geographically complex, and in many cases less prepared for the specific stresses that a megathrust earthquake will impose. The role of tribal nations in the Cascadia preparedness and planning effort is an aspect of the story that often receives insufficient attention in the mainstream coverage of the hazard. The coastal tribal nations of the Pacific Northwest have lived on the Cascadia-affected coastline for thousands of years. Their oral traditions contain accounts of past Cascadia earthquakes and tsunamis that are among the most important sources of qualitative information about the prehistoric behaviour of the system. The Huayet First Nation on Vancouver Island, the Quileute tribe on the Washington coast, the Quinault Indian Nation, the coastal tribes of Oregon, all carry cultural memories of catastrophic shaking and flooding that align with the paleoseismic record of Cascadia ruptures. These accounts describe the ground shaking that preceded the arrival of the ocean, the behaviour of the water during inundation, the characteristics of the retreat after the main tsunami waves, details that are consistent with the geophysical models of Cascadia tsunamis, and that provide a human perspective on events that occurred beyond the range of instrumental observation. The tribal nations are also among the most exposed communities to the Cascadia tsunami hazard, with reservation lands that in some cases sit directly in mapped inundation zones, and with populations that include some of the most economically vulnerable residents of the affected region. The integration of traditional ecological knowledge and oral history into the scientific understanding of the Cascadia system represents an approach to hazard science that has been advocated by researchers at the intersection of Indigenous studies and earth science for years. The practical value of that integration goes beyond the scientific interest of having additional data points about past events. It encompasses the recognition that the communities most at risk from a hazard are also the communities with the deepest historical relationship to that hazard, and that their knowledge and their participation in preparedness planning are not optional supplements to the technical work, but essential components of a comprehensive approach to reducing the harm the hazard will cause when it next occurs. The scientific monitoring network that recorded the Canadian earthquake continues to evolve. New seismic stations are being added to improve coverage in areas where the existing network has gaps. New GPS receivers are being deployed to fill spatial gaps in the geodetic monitoring. New ocean bottom instruments are being developed and deployed as funding allows. The Shake Alert system continues to be refined, with improvements to the algorithms that estimate earthquake magnitude and location from the first arriving waves, reducing the time between earthquake origin and alert delivery, while also reducing the false alarm rate. Each improvement in the monitoring infrastructure increases the scientific community's ability to detect and characterize earthquakes in the Cascadia zone, to track the slow deformation of the locked subduction interface, and to provide the most accurate possible characterization of the seismic hazard to the planners and engineers and emergency managers who translate that characterization into protective actions. The earthquake that just hit Canada will fade from the news cycle within days. The aftershock sequence will continue at a declining rate for weeks to months, occasionally producing a felt earthquake that will briefly refresh public awareness before again receding. The scientific analysis of the event will continue for months, producing journal articles that will be read by the community of researchers studying the Cascadia system, and that will modestly refine the collective understanding of the stress state of the region. The emergency managers who activated their response protocols will debrief their operations, identify lessons learned, and adjust their procedures. The politicians who held press conferences in the days after the earthquake will move on to other issues. The residents of British Columbia and Washington and Oregon who felt the shaking will mostly resume their lives, carrying a slightly heightened awareness of the seismic environment they live in that will gradually fade to the background level over weeks and months. The Cascadia subduction zone will not notice any of this. The Juan de Fuca plate will continue to subduct beneath North America at approximately 4 centimeters per year, indifferent to the scientific attention it receives, indifferent to the preparedness investments being made in the communities above it, indifferent to the oral traditions that record its previous behaviour and the instrumental records being accumulated to characterise its current state. The locked interface will continue to accumulate strain. The episodic tremor and slow slip events will continue to occur approximately every 14 months at the deep transition zone. The GPS receivers will continue to record the millimetre-scale deformation of the surface. The ocean bottom pressure sensors will continue to watch the sea floor. The seismometers will continue to record every tremor and micro-earthquake and distant teleseismic event that passes through the crust of the Pacific Northwest. And somewhere in the data stream flowing continuously from that network, in the patterns of tremor and slow slip and surface deformation that the scientific community is learning with increasing sophistication to read, the subduction zone is telling its story. A story that has been unfolding for millions of years. A story that has chapter breaks separated by hundreds of years of apparent quiet, followed by minutes of catastrophic release. A story that the paleoseismic record has documented across 10,000 years of episodes, each one reshaping the coastline, each one recorded in the sediment layers of coastal marshes and the oral traditions of the people who lived through them and survived to tell their descendants what the earth had done. The next chapter of that story has not yet been written in the sediment. It has not yet reshaped the coastline. The trees that will be drowned by the coastal subsidence of the next megathrust earthquake are still growing. The children who will be the oldest survivors of that event, the ones whose testimony will be recorded by researchers in the decades after it occurs, are alive today. Some of them in elementary school in Seattle or Portland or Vancouver, practicing earthquake drills they hope they will never need to use outside of practice. The buildings that will stand and the buildings that will fall are mostly already built, their fates largely determined by when they were constructed and how, though some fraction of the most vulnerable among them will be retrofitted before the earthquake arrives, and some fraction of the population that would otherwise be in those buildings when the shaking begins will be somewhere else because a warning reached them in time. The scientists who went quiet when the Canadian earthquake data came in have gone back to work. The data from the event is being processed, analysed, incorporated into the models. The papers are being written. The hazard assessments are being reviewed to determine whether any update is warranted based on the new information. The monitoring continues, the understanding grows, incrementally, imperfectly, never fast enough given the scale of what is being studied and the consequences of what it will eventually produce. The ground moved in a place it was never supposed to move, and the planet, which keeps its own timeline regardless of the timelines of the species currently living on its surface, continued its slow conversation with itself in the language of tectonic stress and crustal deformation and frictional failure. A conversation that has been ongoing for billions of years, and that the Canadian earthquake was one brief, local, geologically insignificant sentence in the middle of a paragraph that will not end within any human time frame currently imaginable. The scientists are listening. They have been listening for decades. They will keep listening, and what they are hearing, in the data from the earthquake that just hit Canada, and in all the data that preceded it, and in all the data that will follow it, is a system that is not finished speaking. The specific character of what the system is saying changes depending on which instrument you are reading and which timescale you are examining. On the timescale of seconds, the seismometers speak. They record the passage of seismic waves through the crust, waves generated by the Canadian earthquake, and by thousands of smaller events that occur in the region every year, most of them too small to be felt, but all of them carrying information about the stress state of the crust and the properties of the material the waves are travelling through. The velocity at which seismic waves travel through rock is sensitive to the stress the rock is under. Stressed rock transmits waves differently than unstressed rock. Networks of seismometers arranged in arrays can, in principle, detect changes in wave velocity that reflect changes in crustal stress over time. This technique, called seismic velocity monitoring, or ambient noise tomography, depending on the specific implementation, has been applied to the Cascadia region, with results that are scientifically interesting and that are still being interpreted in terms of what they reveal about the approach of the system toward the next rupture. On the timescale of days to weeks, the GPS receivers speak. They record the accumulated motion of the surface, integrating the continuous slow deformation of the locked subduction zone into position changes that accumulate over months and years to produce the clear signal of interseismic strain. The GPS data for the Pacific Northwest has been accumulating since the mid-1990s, giving scientists approximately 3 decades of continuous surface motion records to work with. 3 decades is a short time compared to the recurrence interval of Cascadia megathrust earthquakes. It is long enough to establish the background rate of interseismic deformation with good precision and to detect departures from that background rate when they occur. The departure detected in the weeks preceding the Canadian earthquake, the subtle acceleration in surface motion that only became recognisable in retrospect, illustrates both the potential and the limitation of this monitoring approach. The potential is real, the limitation is equally real. A signal that can only be recognised after the fact, that is buried in measurement noise during the period when it would be actionable, is a scientifically interesting observation, but not a practical warning. On the timescale of months, the episodic tremor and slow slip events speak most loudly. The approximately 14-month periodicity of ETS events in the Pacific Northwest is one of the most remarkable regularities in tectonic science anywhere on Earth. The regularity suggests a physical process that operates on a clock-like mechanism, cycling through stress accumulation and release at the deep transition zone, with a consistency that has no obvious analogue in other tectonic settings. The physical mechanism behind this regularity is not fully understood, which is itself a scientifically interesting observation. The most widely accepted model involves the properties of the fault zone material at the specific pressure and temperature conditions of the deep transition zone, where minerals that are brittle at shallow depths begin to deform plastically, and where the presence of high-pressure fluids plays a critical role in controlling frictional behaviour. The fluids come from the dehydration of the subducting oceanic crust as it descends to greater depths and temperatures. Water bound in the crystal structure of oceanic minerals is released as those minerals transform at high pressure and temperature, generating free water that migrates into the fault zone and reduces the effective normal stress on the fault surface, allowing slip to occur at lower shear stress than would otherwise be required. The connection between these deep, fluid-driven slow slip events and the behaviour of the shallow locked zone above them is a question of central importance for Cascadia hazard assessment, and one that the scientific community has been working to answer since ETS was first recognised as a phenomenon. The slow slip at depth does not relieve the stress on the shallow locked zone directly. The shallow locked zone, the portion of the subduction interface that will eventually rupture in a megathrust earthquake, is at different depths and different temperature and pressure conditions than the slow slip zone. But the stress changes produced by slow slip at depth do propagate upward into the overlying crust and do incrementally load the shallow locked zone. Each ETS event adds a small stress increment to the locked zone. 325 years of ETS events have collectively transferred a significant amount of stress to the locked zone above them, in addition to the stress being transferred by the ongoing plate convergence itself. The question of whether an ETS event could directly trigger a megathrust earthquake, rather than simply contributing incrementally to the stress on the locked zone, is one that seismologists have examined carefully and that remains open. The mechanical conditions required for an ETS event to cascade upward into a megathrust rupture involve the slow slip front reaching a portion of the locked zone that is critically stressed and close to failure. If the locked zone is sufficiently loaded that only a small additional stress increment is needed to initiate rupture, and if an ETS event provides that increment, then an ETS event could, in principle, trigger the megathrust. The probability of this happening in any given ETS cycle depends on how close to failure the locked zone currently is, a quantity that cannot be directly measured. What can be said is that the probability of this triggering relationship increases as the interseismic period progresses and as the cumulative stress on the locked zone grows. 325 years into an interseismic period, with an average duration of 240 years, the locked zone is almost certainly more stressed than it was 100 years ago, and the probability of any given ETS event triggering a cascade toward megathrust rupture is correspondingly higher. The specific ETS event that occurred approximately 3 months before the Canadian earthquake was notable for several reasons that the scientific teams monitoring the network documented at the time. The duration of the event was slightly longer than the median for the region. The spatial extent of the slow slip, as imaged by the GPS data, was slightly larger than the median. The tremor rates during the event were elevated compared to recent ETS events. None of these characteristics individually moved the event outside the range of normal variability that the 3-decade instrumental record encompasses. But the combination of a longer duration, larger spatial extent, and elevated tremor rates in a single ETS event is a combination that sits at the upper end of the observed distribution for this system. And the earthquake that occurred 3 months after that event, on a fault in the overriding plate at a depth consistent with stress transfer from the slow slip zone, is now part of the context within which that ETS event will be interpreted. Whether the connection is causal, whether the ETS event loaded the fault that subsequently ruptured, is a question the post-event scientific analysis is specifically designed to address. The paleoseismic record of ETS-like events before the instrumental era is, by definition, inaccessible through direct measurement. ETS events do not leave a clear signature in the sedimentary record the way megathrust earthquakes do. The coastal marsh stratigraphy that records sudden subsidence during megathrust ruptures does not record the millimeters of slow slip during ETS events. This means that the relationship between ETS event behavior and megathrust earthquake timing across the full 10,000-year paleoseismic record cannot be evaluated directly. It can be modelled. The model suggests that ETS events should have been occurring throughout the Cascadia interseismic periods recorded in the paleoseismic record, that they should have been loading the locked zone incrementally throughout each interseismic period, and that the accumulated loading from hundreds of ETS cycles over the course of each interseismic period should have been a significant contribution to the total stress on the locked zone at the time of each megathrust rupture. But this is a model inference, not a direct observation. The distinction between model inference and direct observation is one that the scientific community maintains carefully, and that the public communication of earthquake hazard sometimes blurs in ways that erode the credibility of the science when the model inference turns out to be wrong in a specific detail. The history of earthquake prediction research is littered with examples of promising signals that turned out not to be reliable precursors, of correlations that held for a period and then failed, of mechanisms that seemed physically plausible but did not survive rigorous testing against data. the scientific community has become appropriately cautious about claiming predictive capability for earthquake timing as a result of that history. The caution is scientifically warranted. It creates a communication challenge when the honest scientific message is that a system is in an elevated state of hazard, but that the timing of the next major event cannot be specified. That message is accurate. It is also unsatisfying for an audience that wants to know whether they should be worried about the next 10 years or the next 10 minutes. The answer for the Cascadia system in the present moment is that both timescales deserve attention, but for different reasons and in different ways. The next 10 minutes deserves attention in the sense that a Cascadia megathrust earthquake could, in principle, occur at any time, including in the next 10 minutes, and that the response to the shaking of such an earthquake, the drop, cover, hold on response to the shaking, and the immediate evacuation of coastal areas after the shaking stops, needs to be automatic and practiced, rather than deliberate and planned in the moment. The next 10 years deserves attention in the sense that the preparedness investments that determine outcomes during and after a major earthquake, the retrofit of vulnerable buildings, the hardening of lifeline infrastructure, the establishment of vertical evacuation structures, the development of community preparedness and recovery capacity, all operate on timescales of years and require sustained political will and sustained funding to complete before the earthquake arrives. The window of opportunity for preparedness investment is not unlimited. Every year that passes without a Cascadia megathrust earthquake is a year in which preparedness investments can be made. Every year that passes is also a year in which new buildings are constructed, in which the population of the hazard zone grows, in which the inventory of infrastructure exposed to the hazard expands. The net effect on the preparedness gap, the difference between the current state of readiness and the state of readiness that would minimize harm from a major earthquake, depends on which is growing faster, the preparedness investments or the exposure. In the Pacific Northwest, the evidence of the past 2 decades suggests that both are growing, that meaningful preparedness progress has been made, and that the exposure is growing at least as fast as the preparedness in most metrics. The preparedness gap has not closed. In some dimensions it has widened, as population growth has outpaced the expansion of shelter capacity, evacuation infrastructure, and community preparedness program reach. The federal role in Cascadia preparedness has been substantial in some areas and inadequate in others. The USGS Earthquake Hazards Program provides the scientific foundation for seismic hazard assessments and building code development. FEMA provides funding for preparedness programs, hazard mitigation grants, and post-disaster recovery assistance. The National Tsunami Hazard Mitigation Program coordinates tsunami preparedness across the Pacific-facing states and territories. These programs represent genuine federal investments in reducing Cascadia earthquake and tsunami risk. They are also programs whose budgets have been subject to the same pressures that constrain all discretionary federal spending, pressures that have limited the pace at which monitoring networks can be expanded, research programs funded, and preparedness initiatives implemented at the community level. The economic case for Cascadia preparedness investment is, by the standard metrics of benefit-cost analysis, among the strongest that exist for any natural hazard mitigation program in the United States. The projected losses from a Cascadia megathrust earthquake, estimated by various studies in the range of tens to hundreds of billions of dollars, depending on the specific scenario and the metric used, dwarf the cost of the preparedness investments that would significantly reduce those losses. Retrofitting every vulnerable building in Seattle and Portland before the earthquake would cost billions of dollars. The alternative, rebuilding those buildings after they collapse in the earthquake, and managing the associated casualties and displacement, costs more, spreads the cost over a much shorter period, and adds the incommensurable costs of lives lost and communities disrupted in ways that economic analysis cannot fully capture. The benefit-cost case for preparedness is clear. The political case is harder, because the benefits are realised in a future earthquake that has not yet occurred, and that the political system finds difficult to plan for in competition with present problems that are immediate, visible, and politically pressing. The Cascadia earthquake that will eventually occur will not wait for the political case to become easier. It will not wait for the preparedness gap to close. It will not wait for the monitoring network to achieve complete coverage, for the building retrofit programs to be completed, for the tsunami evacuation structures to be built in every at-risk community, for the population of the hazard zone to complete the transition from general awareness to specific practice preparedness. It will occur when the accumulated stress on the locked interface exceeds the frictional resistance that has held the Juan de Fuca plate in place since January of 1700. That moment could be decades away. It could be tomorrow. The Canadian earthquake that just occurred is a reminder that the system is not resting, that the stress is accumulating, that the crust is responding to the approach of the rupture threshold in ways that are detectable by the instruments that monitor it, and that the time available for preparedness investment is finite, even if the precise length of that time is unknown. The scientists who monitor the Cascadia system have a word for the state they are trying to characterize. They call it the current state of the seismic cycle. The seismic cycle is the full sequence from one megathrust earthquake to the next, encompassing the interseismic period of strain accumulation, the co-seismic release of that strain during the earthquake, and the post-seismic period of aftershock activity and viscoelastic relaxation that follows. Within the interseismic period, the seismic cycle has a character that evolves over time. Early in the interseismic period, the stress on the locked zone is low because the previous earthquake released most of the accumulated strain. As the interseismic period progresses, the stress on the locked zone grows. Late in the interseismic period, the stress is high, the locked zone is close to failure, and the probability of triggering events, of stress perturbations from other earthquakes, or from ETS events pushing the locked zone over its failure threshold, is elevated. The Cascadia system is late in its interseismic period, 325 years late, relative to the average recurrence interval. The state of the seismic cycle is one of elevated stress, elevated triggering probability, and elevated awareness within the scientific community that the transition from interseismic to co-seismic is closer than it was at the beginning of the instrumental record. The awareness within the scientific community has not been matched by proportional awareness within the general population of the Pacific Northwest, despite years of science communication effort. The 2015 New Yorker article that brought the Cascadia hazard to national attention produced a brief surge of public engagement with earthquake preparedness in the region. Sales of earthquake preparedness supplies increased. Emergency management agencies reported increased interest in their preparedness programs. The attention faded as public attention to low-probability, high-consequence risks tends to fade in the absence of a triggering event that refreshes the salience of the hazard. The Canadian earthquake is a triggering event. It is a reminder. Whether the reminder will translate into sustained engagement with preparedness, or whether it will produce a brief spike in attention followed by the same gradual fade that followed the New Yorker article, depends on factors that the scientific community cannot control and can only observe. The psychology of living with a low probability, high consequence risk is one of the most studied topics in the behavioral science of natural hazard preparedness. Research consistently shows that humans are not well calibrated for reasoning about low probability events, particularly when the consequences are catastrophic and the time frame is long. The cognitive heuristics that serve people well in everyday risk assessment tend to fail for rare catastrophic events. The availability heuristic, which assesses risk based on how easily examples come to mind, produces underestimation of risks that are rare and overestimation of risks that have been recently salient. The optimism bias leads people to believe that bad outcomes are more likely to happen to others than to themselves. The status quo bias leads people to avoid taking preparedness actions because taking action requires effort and change, while maintaining the current state requires nothing. All of these cognitive tendencies work against the kind of sustained, motivated engagement with earthquake preparedness that would significantly reduce harm from a Cascadia event. The behavioral science research on what works to overcome these tendencies in the context of earthquake preparedness has identified several factors that are associated with higher preparedness levels. Direct personal experience of a significant earthquake is the most powerful predictor of preparedness behavior, which is partly why communities in California that have experienced significant earthquakes tend to have higher preparedness levels than communities in the Pacific Northwest that have not experienced a comparable event within living memory. Social influence, the observation that neighbors and community members are taking preparedness actions, increases individual preparedness behavior. Trusted messenger effects mean that preparedness messages from sources that individuals already trust, community leaders, local employers, religious institutions, are more effective than messages from government agencies alone. And simplicity, the provision of a small number of specific, concrete preparedness actions, rather than a comprehensive list of everything that would be ideal, increases the probability that any action will be taken. The earthquake preparedness communication campaigns that have been most successful in the Pacific Northwest have incorporated these behavioral science findings to varying degrees. The Great Shakeout Earthquake Drill, which organizes simultaneous practice of the drop, cover, hold on response by participants across the region and around the world on a specified date each year, uses the social influence factor by making preparedness a visible community activity. The 7 Steps to Earthquake Safety campaign provides a simple, sequenced action list that reduces the cognitive load of engaging with a complex preparedness topic. The integration of earthquake preparedness into school curricula reaches children in an institutional setting where practice is normalized and where the social influence of peers reinforces the behavior. None of these campaigns has fully closed the preparedness gap. All of them have contributed to the measurable progress in preparedness levels that surveys in the Pacific Northwest have documented over the past decade. The Canadian earthquake will contribute to this ongoing effort in ways that depend on how the event is communicated and how that communication connects to actionable preparedness steps. A communication that focuses exclusively on the scientific aspects of the event, the fault mechanism, the depth, the stress transfer implications, will reach an audience that is already engaged with the topic and will reinforce their understanding without necessarily expanding the circle of prepared individuals. A communication that connects the scientific context to specific, concrete preparedness actions that translates the information about the Cascadia system's current state into the question of what an individual household can do this week to be better prepared, has the potential to convert scientific awareness into behavioral change. The difference between those two types of communication is the difference between informing the already engaged and expanding the prepared population. The prepared population in the Pacific Northwest is meaningfully larger than it was 20 years ago. The prepared population is still a minority of the total population of the Cascadia hazard zone. The gap between those two facts is where the harm from the next Cascadia earthquake will be concentrated. Not exclusively in that gap, because even well-prepared individuals and communities will experience harm from a magnitude 9 earthquake and the tsunami it generates, but disproportionately in that gap, in the communities and households and structures that have not taken the actions available to them to reduce their vulnerability, because those actions have not been taken yet. The seismometers are still running, the GPS receivers are still measuring, the ocean bottom pressure sensors are still watching the seafloor, the shake alert system is still armed, the paleoseismologists are still coring the coastal marshes and reading the sediment layers. The earth scientists studying the Cascadia system are still at their desks, still watching the data stream that flows continuously from the monitoring network, still building incrementally toward a more complete understanding of a system whose behavior they can characterize with increasing precision and whose timing they cannot predict with any useful specificity. The aftershocks from the Canadian earthquake are still occurring, declining in rate according to the Omori-Utsu law, adding small additional data points to the growing record of seismic activity in the region. The Juan de Fuca plate is still subducting, 4 centimeters per year. The locked interface is still locked. The strain is still accumulating. The episodic tremor and slow slip events will occur again in approximately 11 months, loading the deep transition zone with another cycle of slow slip and transferring another small stress increment to the shallow locked zone above. The cycle will continue. The monitoring will continue. The preparedness work will continue. The political negotiations over retrofit programs and evacuation infrastructure and monitoring network expansion will continue. And the Cascadia subduction zone, indifferent to all of this activity on the surface above it, will continue its slow, inexorable convergence, storing the energy of continental collision in the locked interface between 2 tectonic plates, waiting for the friction to fail. The Canadian earthquake that scientists are still analysing, whose aftershocks are still occurring, whose stress transfer implications are still being modelled, is a sentence in the middle of a very long story. The story began when the Juan de Fuca plate first began subducting beneath North America millions of years ago. It has included hundreds of megathrust earthquakes that no human observed and that are known only from the geological record they left behind. It included the earthquake of January 26, 1700, which was witnessed by the indigenous peoples of the Pacific Northwest coast, and whose memory is preserved in their oral traditions, and which was recorded unknowingly in the tide gauges and historical documents of Japan by the tsunami it generated. It has included the decades of scientific investigation that have characterized the Cascadia system with increasing precision. It includes the Canadian earthquake that just occurred, and the scientific and public response it has generated. And it will include, at a time that cannot be specified, but that the weight of evidence suggests is not in the distant future by geological standards, the next megathrust rupture, the next magnitude 9 or greater earthquake, the next Cascadia tsunami. That rupture will be the next major chapter. The communities of the Pacific Northwest are writing their response to that chapter now, in every retrofit completed, and every evacuation route improved, and every preparedness drill conducted, and every emergency plan updated. The quality of that response, measured in lives protected and communities preserved and recovery accelerated, will be determined by the accumulated effect of all those actions taken before the earthquake arrives. The time available for those actions is finite. The actions themselves are knowable, fundable, and executable. The gap between knowing what needs to be done and having done it is the gap that the Canadian earthquake, in its small way, has briefly illuminated for anyone paying attention. The monitoring networks that detected and characterized the Canadian earthquake within minutes of its occurrence represent the current frontier of humanity's ability to understand and respond to the tectonic forces that shape the surface of the planet. That frontier has advanced dramatically in the decades since the first seismometers were deployed, and has continued to advance in the years since GPS revolutionized geodetic monitoring, and ocean bottom instruments made it possible to watch the seafloor directly. The pace of advance has accelerated as computational power has increased, as data storage costs have fallen, as machine learning techniques have been applied to the enormous datasets generated by modern monitoring networks, and as international scientific collaboration has made it possible to pool data and expertise across national boundaries in ways that no single national program could achieve alone. The next frontier in Cascadia monitoring is the integration of multiple data streams into a unified, real-time picture of the state of the subduction system that can be interrogated by scientists and by automated systems simultaneously. The individual instruments, the seismometers and GPS receivers and ocean bottom sensors, each contribute a partial view of the system. Combining those partial views into a coherent picture of the current stress state, the current deformation pattern, and the current seismicity distribution requires sophisticated data integration and modelling that is still being developed. The tools for this integration are advancing. Machine learning approaches to detecting and classifying seismic signals have dramatically increased the number of small earthquakes and tremor episodes that can be extracted from noisy data, effectively increasing the density of the monitoring network without adding new instruments. Automated anomaly detection algorithms can flag departures from the background behaviour of GPS time series or seismicity rates in near real time, potentially reducing the time between when an anomalous signal occurs and when it comes to scientific attention. Whether any of these advances will ultimately enable earthquake forecasting with the specificity that would allow meaningful protective action in advance of a major Cascadia event remains an open question. The honest scientific answer is that such capability does not currently exist, and that there is no consensus within the scientific community that it will exist on any definite future timeline. The physics of fault rupture may impose fundamental limits on the predictability of earthquake timing that no amount of additional monitoring data or computational sophistication can overcome. Or there may be detectable precursory signals in the behaviour of the fault system in the months and weeks and days before rupture that current monitoring is too sparse or too noisy to resolve, but that a denser and more sophisticated monitoring network could detect reliably. The scientific community does not know which of these possibilities is closer to the truth, because the question has not yet been answered, by sufficient data from sufficiently large earthquakes, monitored by sufficiently dense networks. The Canadian earthquake provides a small increment of data that is relevant to this question. The retrospective analysis of the GPS data preceding the event, which revealed the subtle acceleration in surface motion that was not detectable in real time, is exactly the kind of precursory signal that earthquake forecasting research is searching for. The fact that it was detectable in retrospect, but not in real time, is a statement about the current state of detection capability, not a fundamental statement about whether such signals exist. Improving the ability to detect such signals in real time, to distinguish them from the background noise of normal geodetic variability, and to interpret them correctly in terms of the physical processes they reflect, is one of the central research goals of the earthquake hazard community. Progress is being made. The pace of that progress is uncertain. The time available before the next Cascadia megathrust earthquake is unknown. The intersection of those two uncertainties is where the preparedness imperative lives. The ocean does not care about these uncertainties. The Juan de Fuca plate moves at 4 centimeters per year, regardless of whether the scientific community understands the precursory signals of its eventual megathrust rupture. The locked interface accumulates stress, regardless of whether the monitoring network is dense enough to detect the accumulation in real time. The sediment layers in the coastal marshes of the Pacific Northwest continue to record the passing years of the current interseismic period, regardless of whether the paleoseismologists coring those marshes find funding for the next field season. The planet operates on its own schedule, indifferent to the epistemological uncertainties of the species currently trying to understand it. The species trying to understand it includes the scientists who went quiet when the Canadian earthquake data arrived. They went quiet because the data was telling them something important about the state of the system they have devoted their careers to monitoring. They are not quiet anymore. They are writing papers, updating models, briefing emergency managers, reviewing the monitoring network performance, identifying gaps in the data coverage that the Canadian earthquake has revealed, and designing the next generation of instruments and algorithms that will reduce those gaps. They are doing the work that the Cascadia system demands of them, with the urgency that 325 years of accumulated interseismic stress should inspire, and with the honesty about what they know and what they do not know that the history of earthquake prediction research has taught the community is the only scientifically and ethically defensible approach. The people living above the locked interface, in Seattle and Portland and Vancouver, and in the smaller cities and towns and tribal communities distributed across the Cascadia hazard zone, are also doing work. Some of them are retrofitting their buildings, some are building earthquake preparedness kits, some are learning their evacuation routes, some are attending community preparedness meetings, some are advocating for stronger building codes and faster retrofit programs. Some are doing none of these things, not because they do not care, but because the distance between caring about a low probability future risk and taking action to reduce it is a distance that the normal pressures of daily life make difficult to cross. The Canadian earthquake has shortened that distance, briefly, for some portion of the population. The question that the preparedness community is always asking is how to maintain the momentum that significant seismic events create, how to translate the brief period of heightened salience into lasting behavioural change, how to close the preparedness gap faster than the exposure grows. The answer to that question is not fully known. The direction of the answer is. It involves sustained institutional commitment to preparedness programs that reach people where they are. It involves building codes that are adopted quickly and enforced consistently. It involves retrofit programs that are mandatory, funded, and executed on timelines that the seismic hazard demands, rather than timelines that political convenience allows. It involves tsunami evacuation infrastructure that is built before the tsunami, not after. It involves monitoring networks that are expanded and maintained and continuously improved. It involves scientific communication that is honest about uncertainty and clear about the actions that uncertainty does not prevent. None of this is new information. The Cascadia preparedness community has been saying all of it for years. The Canadian earthquake has given those words a fresh context, a renewed urgency, a specific recent event to point to as evidence that the system is not dormant and that the window for preparedness action is open now and will not remain open indefinitely. The window has been open since 1700. It is still open. The question is how much of it the communities of the Pacific Northwest will climb through before it closes. 2352. Claude responded, "The ground beneath the Pacific Northwest is not resting. The ground beneath the Pacific Northwest is not resting. It never was. 325 years have passed since the last time the Juan de Fuca plate lost its grip on the North American plate and released 3 centuries of accumulated energy in a matter of minutes. 325 years of 4 centimeters per year. 325 years of a locked interface holding, storing, building toward a threshold that the geological record shows it has crossed before, repeatedly, across 10,000 years of sediment layers and drowned forests and oral traditions carried by the peoples who lived through the previous chapters and survived to describe them to their descendants." The Canadian earthquake that scientists are still analysing did not answer the question everyone is actually asking. It never could. No single earthquake can answer the timing question. The timing question may not be answerable by any instrument or algorithm currently in existence. What the earthquake did was speak. It added its sentence to the ongoing conversation between the tectonic plates and the monitoring networks trying to read them. It reminded the scientific community, and briefly the public, that the conversation is still happening, that the system is not quiet, that the stress in the crust above the locked interface is elevated and responding and real. The seismometers are still running, the GPS receivers are still measuring, the ocean bottom sensors are still watching the seafloor from below. The scientists who went quiet when the data arrived have gone back to their desks. The preparedness gap that determines how many people survive the next major Cascadia event and how quickly the communities above the locked interface recover from it is still open, still closable, still demanding the kind of sustained attention that low probability, high consequence risks almost never receive until after the consequence has already arrived. Somewhere beneath the cold water off the coast of British Columbia, the Juan de Fuca plate is moving. 4 centimeters this year, 4 centimeters next year. The friction that has held since 1700 is holding still. And the only honest thing that science can say about what happens next is that the friction will not hold forever. That when it fails, the failure will be sudden and total, and will reshape the coastline the way it has reshaped it before. And that the time between now and that moment is finite in a way that 325 years of geological patience makes very difficult to feel, but very important to act on. The next warning will not come from a seismometer. It will come from the ground itself, shaking, telling 40 million people on the Pacific coast of North America what the scientists have been trying to tell them for decades. The question is whether they will be ready.